everyone, this is Dr. Sirisha, working as Associate Professor in Institute of Aeronautical Engineering College. Today we are going to discuss about spanning trees and graph traversal techniques as well as Prim's algorithm we are going to see in particular. Okay, so coming to spanning trees. First of all, going to spanning trees, you need to understand what a graph is. First of all, a graph, let me draw a small picture for the same. Have a look at this one. This is a graph with 5 nodes or vertices. You can call it in either way. So a naming will be there for each and every node. Okay, so this is a graph G with 5 nodes, right? So graph is a collection of nodes and the edges which it has. Edge is nothing but a line or a line which connects two nodes, right? So that is the basic definition of a graph. Coming to spanning tree, what is a spanning tree? Tree itself tells that it should not have any loops, any parallel edges, no circuits, right? These 3 points should be there. So spanning tree is a collection of edges in a graph, minimally connected, or you can say minimally connected ones, in such a way that they do not form any cycles or loops should not be there. For example, in this one, for the same one, A, E, D, C, and B, I'm going to connect. I'm going to use only the edges which I have in my hands. I'm not going to introduce any new edges. So have a look at this one. This is a spanning tree. A, E. You can have any number of spanning trees for a given graph. So it is a collection of vertices with minimum possible edges. You are going to convert a graph into a spanning tree with minimum possible number of edges. So roughly you can say that if there are n nodes, then you will be having n minus 1 edges. And you can have any number of sparse trees for the same. For example, if I let me remove this edge and make this, even this is a spanning tree. Have a look at this one. If I add this one, even this is a spanning tree. Okay, but I cannot have, even this is a spanning tree. I'm using, have a look at this one, I'm using only the vertices and the edges which I have. And I have not isolated any vertex. That means no node is unused in my structure while converting a graph into a spanning tree. So every connected and undirected graph have at least one spanning tree. Okay. A variation of this spanning tree is minimum spanning tree. When we talk about minimum spanning tree or minimum weighted spanning tree, it means we are talking about a weighted undirected graph. A connected, weighted, undirected graph I'm talking about. Please remember these 3 points when we talk about a minimum spanning tree. The first is it should be connected one. That means all the nodes must be used, and it is undirected, and it is a weighted graph. Got it? It is a weighted graph. Right. So what is a minimum spanning tree? Minimum spanning tree is a spanning tree where when we add the weights of the edges which are present in the spanning tree, it is the least cost. The least cost. The sum of the weights of the edges is minimum. Such a spanning tree is known as minimum spanning tree. And every graph have at least one minimum spanning tree, and you can have more than one minimum spanning tree. Yes, by connecting the weights, it is just a sum of numerical values. If you say 2 plus 2 is equal to 4, 1 even 1 plus 3 is also 4. Am I right or wrong? So you can have more than one minimum spanning tree for a given graph. Then what are the basic properties of a spanning tree? In a connected graph, you can have more than one spanning tree, and all the possible spanning trees of the graph have the same number of edges and vertices. As I said, you should not isolate any vertex, and the edges should not form any cycle, right? And you should not have any cycle. And you need to remember, adding at least one edge to that will make a cycle in it, or removing an edge from the spanning tree will make it a disconnected. So it is minimally connected, maximally acyclic tree. A spanning tree is a minimally connected and maximally acyclic tree. Okay, these are the properties which you need to keep in your mind. Right. Next one, what are the basic properties? Guys, please make a note of these points. These points are very, very important in competitive exam points of view. Whether you take your GATE exam or placements exam, these points are very, very important. Say in an undirected graph, there are n number of nodes, you can have maximum n power n minus 2 number of spanning trees. N power n minus 2 number of spanning trees. And each spanning tree has n minus 1 number of edges if it is having n number of nodes. From a complete graph, we're removing maximum e minus n plus 1 edges, right? We can construct a spanning tree. Then what is e over here? E is nothing but your number of edges. E is the number of edges. Please do remember these key points, guys, when you construct a spanning tree, right? In bits also you get these type of questions a lot. Then where we use these spanning trees is another important question. Okay, spanning trees are used in cases wherever we use networks. Networks come into the picture. Whether it can be computer science domain, civil domain, mechanical domain, whatever the domain you take, wherever there is a point of connectivity, like telecommunication networks, connectivity, whether it is wired or unwired, whatever. If there is a connection between things, we can bring a graph of it. It is a form of a graph. It has its own topology, right? So transportation networks, water supply networks, everywhere, wherever. Generally, people say that every problem in this world can be converted into a graph. Can be. It means every problem, what do you think? Every problem is a standalone one. It is linked to another one. It was a byproduct of some action, right? So when you connect all the dots, you'll get a graph, right? So the basic application of spanning tree is networks. You name the domain, networks. Okay. So the next important will be cluster analysis. Then what do you mean by cluster? Cluster is nothing but a group which share same property. Or you can say, if you have pebbles in your hand, if you want to separate them or make groups of them based upon their colors, the attribute over here is color, then each and everyone is a cluster, right? If you want to make clusters or based upon their shapes, like triangles in one bag, squares in one bag, circles in one bag, so based upon a property of shape, you have made clusters. So analysis of these clusters also is a concept of graphs. Coming to NP hard problems, the basic traveling salesperson problem, where a person wanted to travel from one city to another. He is supposed to cover n cities, and he wanted to see that he do not touch a city repeatedly. So he wanted a minimum path between each and each and every city so that he need not travel for much distance. So these problems are addressed by graph theory. Right? I hope you understood that. Basic applications of graphs. Wherever you have a problem that with interconnections, you can construct a graph and thereby a spanning tree of it. Spanning tree will give you the shortest distance, the connectivity in computer networks. When we send data from a source to destination, the packets may get dropped due to congestion. So generally the algorithms in such a way that they go for another route to reach the destination. Right? The shortest path will be given by the spanning trees. Right? So coming to the minimum spanning tree. As I said, it is a variation of your spanning tree where you are going to add the weights on the edges of the tree, spanning tree, and its value should be the minimum. Its value should be the minimum. So it is also known as minimum weight spanning tree. It's a minimum weight spanning tree. And the 3 points which you need to consider are weighted, connected, and undirected. So we are going to apply this minimum spanning tree concept on this particular kind of graph. Okay, so and you can have any number of minimum spanning trees, minimum weighted spanning trees. As I said earlier, it's not a unique one. If I start constructing a minimum spanning tree using one node, you are constructing with the same node, our paths may not be the same, right? So minimum spanning tree is the sum of weights given to each edge of the spanning tree. Okay, it should be minimum. Then it is known as minimum spanning tree. And we can construct MSTs using greedy algorithms. Greedy algorithm is generally used to get optimized solution, to optimize any problem. So what do you mean by optimization? Why we call it greedy? So let me give you a short story to explain you the same. For example, your tutor wants to get a feedback. From after delivering 10 classes. He wants to get feedback from you. How he is going to do that. So is he going to call all the students and get, did you like it or not? Did you like it or not? Though it's a hectic process, next to impossible. If it is a Zoom session where hundreds of students are connected, it is a problem which is next to, right? Impossible. So a better option will be he collects the data. Daily he collects the data of these 10 lectures, the number of people who have attended and who have attempted the assignments which he has given by the end of each and every session. That means 10 classes, 10 sessions, 10 assignments, right? So who attended and how far they were able to get the solutions, the feedbacks, everything, considering everything, right? So out of say 250 students, at least he can pick five students who, based upon the criteria, who have attended all his 10 sessions and they spent full duration, because in the Zoom link you can see that the duration also it is going to give, right? And then they have attempted the assignments and they were able to score it well, everything. That means all possible good quality students, I can say. So 5 good quality students, bring them, talk to them, get the feedback. Alright? So it is nothing but optimization. I'm not talking to a single person. The tutor is not going to talk to a single person and get the verdict whether the session was good or bad. And neither he is going to talk to all the 250 students to get the feedback. He's taking an optimal solution based upon few attributes, right? It's a greedy way of doing the same, right? So greedy methods are used for optimization purpose. Basically, they are used for that purpose, right? So here we can construct a minimum spanning tree. As I said, we can have, if there are n number of nodes, you can have maximum of n to the power of n minus 2 number of spanning trees. But I want a spanning tree with least weight. My concept of greediness is all there, right? So there are two basic algorithms which help us to give a demonstration on minimum spanning trees, how to construct them. In my previous video, I have explained you the Kruskal's algorithm, how to construct a minimum spanning tree using Kruskal's algorithm. In this session, we'll be concentrating on Prim's algorithm. Okay, I hope you understood what is a minimum spanning tree. Basically, what is spanning tree, then minimum spanning tree, and how to construct a minimum spanning tree. We'll be using one of the algorithms, which is Prim's algorithm. Okay, so let me explain you how a minimum spanning tree looks like using this graph. Say the name of this graph, BG. What can be a spanning tree of? Yeah, have a look at this one. This is an undirected, weighted, connected graph which is having 4 nodes. All the nodes are connected, no node is isolated, and each and every edge is bearing a weight, right? It is a weighted one and it is an undirected one, right? So look at the second picture. It is a spanning tree of the given graph, right? Then have to get the cost of it by adding the weights on the edges, which is 11 plus 8 plus 6, which will give you 25. So in this way, you can construct many trees, many spanning trees. Let me construct one more. A, B, C, and D. 8, 7, 1. Even this is a spanning tree. Of cost 16, right? Even this is a spanning tree. Cycles are not there. All the nodes are covered. 4 nodes, 3 edges. Yes, this is a fair one. And its weight is, the new one weight is less than the one which I have shown earlier, whose weight is 25. So have a look at this one. This is the minimum spanning tree. See, previous one was giving 16, now this is giving just 15. So here 8 plus 6 plus 1 will give you 15, right? So this is nothing but a minimum spanning tree. This is, first one is a graph, second one is a spanning tree, and the third one is a minimum spanning tree. It means the least, the minimum weighted, connected, undirected tree, right? So we can construct these minimum spanning trees using Kruskal's as well as Prim's algorithm. Let's look at Prim's algorithm as an example. Okay, let's have a look at this one. First and foremost step that you have to do is remove the loops and a parallel edge which is having a higher weight. Have a look at the graph. Have a look at the node C. It is having a loop with weight 1. Means it is an edge which whose head is a node and its tail is also the same. Okay, so C is having an edge which starts from C and ends with C, and its weight is no way useful for us. So discard it. First remove all the loops. Next comes your parallel edges. Have a look at the edge between A and B. A and B share 2 edges. One is of weight 6 and the other is of weight 9. Right? Then which one you have to choose? You have to choose the one with minimum weight. Why? Because I'm trying to construct a minimum spanning tree, not a maximum one. Right? So discard 9 and 1 and the first hand. Then perform the Prim's algorithm. Okay, then how this algorithm works. You choose any arbitrary node as the root node, or you can choose a node or an edge with the least weight. Edge with the least weight and Start constructing the Prim cell. Okay, start constructing MST using Prim cell method, more precisely if I say. Okay, now check outgoing edges and select the one with least cost, and see that it does not form any cycle. If it forms a cycle, discard it. If it does not form a cycle, add it to this span. Okay, you have to repeat the step 3 continuously unless you reach V minus 1 edges, where V is the number of vertices of your graph. Means if you have V vertices, then you will be having V minus 1 edges. You have to see that once you reach V minus 1 edges, then your minimum spanning tree is constructed. Please don't worry, I'll explain you this with 2 examples. Have a look. Have a look at this graph. There are how many nodes? 6 nodes. So the number of nodes is equal to 6. If the number of nodes is 6, then in your spanning tree, how many edges you need to have? 5. Please keep this in mind. That is our deadline. Okay. So from where you have to start? I'm starting with an edge with the least weight, BC. Here you can see BC is having 2, whereas CE is also having 2. Both are having the least weight. So choose one. Okay. Now, C and B are the 2 nodes which are introduced to my spanning tree. Now, look for an edge with the least weight which is connected to B and C. So, one is in this direction from B, from C. Have a look and follow my arrows, guys. So, what are the values that are in your hands? Weights 4, 4, 2, 4 and 3. And which one is the least one? 2. So I'm talking about an edge between C and E. Think, adding this edge to the spanning tree, is it going to form any cycle? If it is going to form, do not touch it. Go to the next lower one. If it is not forming, add it to your spanning tree. That's what I have done. I have added it. Next. Now E has come to the party. Now B, C and E are the disclosed ones. Now what are the edges which are not included in the spanning tree but connected to the nodes? One is going from B, from C, these are the edges. From E, this is the edges. Mane, what are the weights you are having in your hands? 4, 4, 3, 4, 3. Right? So, the recent one which I have added is E. So, the least is 2 3s. Choose one of them and add it to your spanning tree. But please see that it does not form any cycle. Right? So, I'm going to add it. I have added C and D. It is having a minimum weight 3. Right? Enough. Connected ones. Again, now D is joined the party. Okay. So I have an edge from B to A, C to A, C to F, E to F, and D to F. These are all the edges which are yet to be included if required. So their weights are 4, 4, 4, 3 and 3 respectively. Right? So choose a weight in such a way that least weight such a way that adding that weighted edge does not form any cycle. Okay. So what I can do, what can I do? Which edge? 2 3s are there. Anyone you add, chalega. So F is in the party now included in our construction point. Now cycles are not there. Have a look at this one. Now again from B I have an edge going to A, from C to A, from C to F, and the other is E to F. So what are all the weights? 4, 4, 4 and 3. Very good. What is the least weight? Obviously 3 is the least weight. What will happen if I add this one into my spanning tree? If I add this one into my spanning tree, you can see that if I start with C, I can touch E, F, D as intermediate and again reach C. A cycle is formed or not. Even though the edge E to F is having the least weight 3, I cannot add it to my circuit because it is not having the eligibility because it will form a cycle. Coming to the remaining 3 4s, what will happen if I include all are having same weights? You can add anyone if you think in that way. What if I add this 4, an edge between C and F? Again, this is going to form a circuit. If you start from D, touch C, F, and again D, the resultant will be a circuit. So I cannot use the edge C and F. Okay, I am left with the 2. One is from B to A and the other is from C to A. What will happen if I add B to A? Cycle will not be formed. Even from C to A, cycle will not be formed. Either one of them is C and I have included. Have a look at this picture. I'll remove. I'll try to redraw. These are the nodes and the spanning tree which I have constructed looks like this. This is the spanning tree. So how many edges are there in this one? 1, 2, 3, 4, 5. Job done. Okay. Then how to get the minimum weight is the primary question. So add the weights on all the selected edges. You are going to get the minimum weight, which is 14. I hope you understood this example. It's very simple. Start with an edge which is having the least weight and the nodes which are connected to the spanning tree which are connected. Check all the outgoing edges and select the least one. If that least one is not forming any cycle, then add it. If it forms a cycle, discard it and go to the next higher. Okay. Then let me explain you with another example. Have a look at this one. This is much complicated one. Please have a look at the weights. There are totally 9 nodes. Let's write. Nodes is equal to 9. So how many edges should be there? Edges must be 8. 8 edges must be there. Okay. Let me explain you this one. Okay, let me keep it like this. Our benchmark, right? So what is the least one? So you have 4, 8, 11, 8, 2, 7, 1, 6, 2, 4, 7, 14, 10, 9. The least one is 1. So I have added it. So what are all the nodes that you have? 6 and 7 are connected. And what are the outgoing edges which are not a part of our final spanning tree? One is towards 0, other is towards 1, and the next is towards 8. When you're talking about 7, coming to the point of 6, you have an edge towards 8 and edge towards 5. So I have 5 options. One, and let me Collect them 8, 11, 7, 6 and 2 are the weights. Which one is the least one? 2 is the least one. Good selection. Adding this edge to your final spanning tree, is it going to increase or is it going to form a cycle? If it is not going to form a cycle, add it. Okay. Then yeah, let me check whether it is going to form or not. No, add it. Now 5 has joined the set of vertices in my span tree. Now again, let's calculate it. From 7, 8, from 7, 11, from 7, 7, from 6, 6 towards 8, from 5, 4, 14 and 10. These are the weights in my hands. Let me write them. 8, 11, 7, 6, 4, 14, 10. Right? So I hope I didn't miss anything. Right, I didn't miss. So the least one is 4. Where is this edge? It is a connection between node 5 to node 2. Right? So adding this edge, is it going to frame any cycle is my point. If it is not going to frame any cycle, you can add it. Right? Is it going to add any cycle? No, my dear, add it. Now 2 have joined the party. Let's see, once again have a look at all the weights. 7 is having 8, 11 and 7. 6 is having 6, 5, 14 and 10. Coming to 2, it is having a 2, 8 and 7. Let me make a note of it. 8, 11, 7, 6, 14, 10, 2, 8, 7. What is the least one? Least cost is 2. Okay, that means it is an edge between node 2 to 8. Adding this edge to the spanning tree, is it going to form a cycle? Have a look, just have a look, rough sketch. No, it is not going to add any cycle. That means, can I add that to my final spanning tree? Yes, we can add it. Okay, let me add the same. Okay, there it goes. Yes, I have added that. Okay, now 8 has joined the party. Now again start the same process. From 7 I have 8, 11, 7. From 6 I have 6. From 5 I'm having 14 and 10 are the weights. From 2 I have 7 and 8. I hope these are the from 8 I have again a 7 and 6, right? 7 and 6. Yeah, they are already been included, so I'm not going to take duplicates data, right? So what are the values I have? 8, 11, 7, 6, 14, 10, 7 and 8. This is the data I'm having. The least value is 6. What will happen if I take 6? Let me draw a sketch. If I add 6, what will happen? A cycle will be formed. Have a look at this one, my dears. It will form a cycle. So even though 6 is the least one, I cannot consider it. I cannot consider it. Coming to 7. 2 7s are there. Okay. Let me consider a 7 between the nodes 7 and 8. Okay. If I include this 7, what will happen? Start from 2 via 8, reach 7 and you are forming a cycle. Are you forming a cycle or not? Yes. Even this weight 7, that is a weight between your nodes 7 and 8 cannot participate in this spanning tree. The next least one is another 7 which is between 2 and 3. If you include the edge between 2 and 3 bearing a weight 7, is it going to form a cycle? No, it is not going to form a cycle. So we can add it. Selection is done. Add it. Okay, so I hope you might have understood. Even if it is having a lower weight, at times the nodes cannot help us. Okay, repeat the process. 7 is having 8, 11, 7, 6, 14, 10. As 3 has joined the party, 9, 2, and 8. What are all the nodes? The edge between 7 and 8, I cannot use. It is forming a cycle. Okay, 6, I cannot use as it is forming a cycle. Okay, leftovers are 2 8s, right? So the remaining are higher. So one edge is between 1 and 2, the other is between 0 and 7. So selecting either one of them is okay because none of them is going to raise a cycle, right? Choose one. I've chosen between 1 and 2, right? Next, coming to the next part. Part 7, from the node 7, 8, 11 and 7 are the edges. From 6, 6 is the edge. From 5, 14 and 10 are the edges. From 3, 9 is an edge. From 1, 4 is an edge. 11 will be a duplicate. I'm not going to touch it. So what are the values? Which one is the least one? Least one is the edge between 0 and 1, which is 4, right? Including that, is it going to form any cycle? No, it is not going to form any cycle. So I can use it, right? I can use it. Fine. Add it. Very good. Now, again the story starts. From 7, I have 8, 11, 7. From 6, I have 6. From 3, I have 9. From 5, I have 14 and 10. Which one is the least one? Least one is 6, but it is of no use. It will form a cycle. Next least is 7. Even this will form a cycle. What if I include 8? The next list is 8. Am I right? If I include 8, what will happen? This is the point which we need to consider. Let me erase these blunders which are not going to help us. What will happen if I include 8? Let's start with 0. 0 to 1. 1 to 2. 2 to 5. 5 to 6. 6 to 8. 7. 7 to 0. See? Cycle is formed or not? So, adding the edge between 0 to and 7 is not going to help us. Is not going to help us. So, leftovers are 9, which is an edge between 3 and 4. It is going to help us because if you add this one, you will not get any cycle, right? So, add it. Right? So, how many edges you have, my dears? I feel that all the nodes are connected by now. So, how many edges are there? 1, 2, 3, 4, 5, 6, 7, and 8. 8 edges are there. So, there is the story because what is the basic funda which I told you guys to remember? If there are n number of nodes, n minus 1 number of edges will be there, right? So here there are 9 nodes, so 8 edges are there, and the construction of your so-called Prim using Prim's algorithm minimum spanning tree is constructed. Okay, so how to get the minimum weight? As we're talking about weights, our agenda is to get the minimum cost. Add the weights on the selected edges of your minimum spanning tree. 1 plus 2 plus 2, 4 plus 4, 8 plus 7 plus 9, which is 37, which is the least weight, the minimum weight, or the optimal weight in whatever way you can say. So Prim's algorithm is a greedy algorithm. I hope you understood by now why I called it a greedy algorithm. It is a greedy algorithm because at each and every node, at every step, it was it was so critically selecting which least weighted one I need to select so that it does not form a cycle also, right? So that's why Prim's algorithm is known as a greedy algorithm, and it is having advantages when compared to Kruskal's algorithm. Why? Because if you check my previous video, which I have done on Kruskal's, there we have constructed a table which consists of weights, the source node, and the destination node. Right? From in the ascending order of the weights, we have made a list of it, and we started selecting the nodes. For to construct a table, a construction of the table is the first step of Kruskal's algorithm. So to construct a table, you need to have prior knowledge of what are the nodes that are going to participate in the construction of minimum spanning tree. If you practically implement it in computer networks where you are trying to transfer data from source to destination, you need to have the information about all the nodes, the intermediate hubs, bridges, whatever connectors you need. You need to have prior information of that. Then, if some node or some edge goes down due to congestion or some other reason, technical issues, then getting the prior information, doing a loads of homework on that goes in vain, right? So that is a static process. You construct a table, based upon the table you start implementing the things, and this table, if you really implement it practically, it is a dynamic one, right? So which is quite not possible, which is in few cases where the traffic is more, it's not possible. Coming to Prims, you can see it is very dynamic. At each and every stage, it is considering all the neighboring nodes to which it can connect, which are not except the node edges which are not present in the spanning tree. It considers all the remaining edges which are connected and checks for the least weighted one so that it gets the least weight. So in Kruskal's, you need to do prior homework of what are all the nodes that are participating along with their weights. You need to have a prior knowledge of that, but here you need not have that. Need not have that. That is the basic advantage of Prim's algorithm. It is dynamic in nature. Okay, so I hope you understood this session. In this session, we had a brief talk on what a graph is, what is a spanning tree, what is a minimum spanning tree, a few properties of spanning trees we have seen, and we have learnt Prim's algorithm, which gives or which constructs a minimum spanning tree, that is a minimum weighted spanning tree, which will be helpful in networks. For all the disciplines in concept of networks, it helps us. So I end this session with this note, and if you have any further queries, please comment on my comment section and let me know so that we can refine our lectures. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.